So in section A, I'll talk to you about normal force. So normal force is just defined as the component that acts perpendicular to the surface. It is also specifically the component that the surface exerts on an object with which it is in contact. So for example, if we have a table and a box is on the table, we can have that weight of the box, and based on Newton's third law, the weight of the box has to have an equal but opposite reaction, and that equal but opposite reaction is called the normal force. Now we can have different situations that cause different, let's say, normal forces. So we can have, in the first situation, I drew a box just having two forces, which is its own weight and the normal force. And because of this, and because it's also in a horizontal surface, the normal force is equal to the weight of the box because it's opposite force but different direction. Now in situation 2, I drew a box that has two forces. So when pushing on it, the weight and, three forces, the weight and the normal force. And in this case, because it has to be equal but opposite reaction, the normal force is equal to the weight and the pushing force added together. So if someone's pushing, then P plus W will equal to its normal force. Now we can also have a situation where someone is pulling on a rope, pulling the box up. So in this case you have the pull, the normal force, and the weight. So it's opposite of the situation I drew before, where the weight is now equal to the pulling plus the force normal. So let's say I give you the pulling force and the weight. To find the normal force, you just subtract them, 15 minus 11, and that will give you 4. And just know that the pulling is supporting the box, and therefore there's less weight being felt on the box. The less weight, the less heavy you feel, let's say. Okay, so now we go on to apparent weight. So apparent weight is actually in contrast to true weight. Your true weight is your actual gravitational force, and your apparent weight is just kind of what the force the object exerts on the scale with which it is in contact. So what you kind of see on the scale. So in order to best explain this, we can draw out a person on a scale inside an elevator. So if a person is on a scale inside the elevator and the elevator is at rest or with a constant velocity, then the scale will show its apparent weight. Now we can also have an elevator that shows a person accelerating downward, and in this situation the apparent weight will be less than its true weight. And if you kind of think of it logically, when you let me go back here. When you are accelerating downward, you kind of feel a little lighter. Okay, and now we go on to accelerating upward. In this case, your apparent weight will actually feel greater than your true weight. Okay, so now we go on to Newton's second law of motion, which just states that force is equal to mass times acceleration, and force is also equal to the net force, is equal to all the forces added together. So let's say you have a man and its weight is mg, and it also has a normal force pushing upward. We can say that the normal force plus the negative mg is equal to ma, therefore Fn is equal to ma plus mg. Mg in the first equation is negative because it is pointing down. Okay, so this concept question states that a stack of books whose true weight is 165 newtons is placed on a scale in an elevator. The scale reads 165 newtons. From this information alone, can you tell whether the elevator is moving with a constant velocity of 2 meters upward, is moving with a constant velocity 2 meters downward, or is at rest? So what we do know is that the scale reads is actual true weight. Therefore, the elevator is either moving at a constant velocity or it's at rest. But we don't really necessarily know if it's moving upward or downward. There's nothing that really tells us that. The only information that we have is that the scale reads its true weight, so therefore we know that it's at a constant velocity or it's at rest. The second concept question states a 10-kilogram suitcase is placed on a scale that is in an elevator. In which direction is the elevator accelerating when the scale reads 75 newtons and when the scale reads 120 newtons? So right now we have to focus on those slides that I told you, whether apparent weight is greater than your true weight, where does the acceleration go? So if the scale, so if they told us that the weight is mg, so the weight in this case would be 10 times 9.81, so around 100 newtons, and the scale reads 75 newtons. In this case, the acceleration should be downward because the apparent weight is less than the true weight. In the case where the scale reads 120, the true weight, the apparent weight, is actually greater than the true weight, so the acceleration should be pointing upward. So in this problem, it states, in a circus balancing act, a woman performs a headstand on top of the standing performer's head. As the figure shows, the woman weighs 490 newtons and the standing performer's head and neck weighs 50 newtons. It is primarily the seventh cervical vertebrae in the spine that supports all the weight above the shoulders. What is the normal force that this vertebrae exerts on the neck and head of the standing performer before the act and during the act? So with the previous lecture, we learned that the upward force and the downward force must balance each other out, so they kind of have to cancel each other out. So we know that in part A, since the normal force and the weight are just directly perpendicular, the normal force is equal to the weight, so it would be 50. In part B, however, we see that there are two forces pointing downward, and the normal force pointing up, so the normal force will have to equal the addition of the two other forces pointing downward. So you will end up with the normal force being 540. So this problem states a 35-kilogram crate rests on a horizontal floor, and a 65-kilogram person is standing on the crate. Determine the magnitude of the normal force that the floor exerts on the crate and that crate exerts on the person. So here we're kind of looking at individual forces. So here I drew the problem that it states to find the normal force and the weights of each. I just multiplied that by 9.81. So in the first scenario, we have to look at the individual force itself. So the floor exerts on the crate. So only look at the crate and the force. So here we just know that the force normal is equal to the weight. So it's just 35 times 9.81 would equal the normal force. And the same thing goes with the second scenario. You just look at the man and the crate, and that's just 65 times 9.81. And that will give you the normal force of that as well. Okay, so this last question states a rocket blasts off from rest and attains a speed of 45 meters per second in 15 seconds. An astronaut has a mass of 57 kilograms. What is the astronaut's apparent weight during takeoff? So, here we know the velocity and the time, and here I just wrote down that, as I explained to you before, force is equal to mass times acceleration, but it's also the net force is equal to the normal force plus the weight, which is negative in this case as well. So because of this, we know that ma plus mg will equal the normal force, and here I just kind of took out the m, and we know the mass and the g. We just need to find acceleration, but we know how to do that because acceleration is just change in velocity over time, and we know the velocity and we know the time. So here I just did the acceleration, and then you add that to the g, and then multiply it to the m, and that will give you the normal force of 730 newtons.